Alright guys, today I'll take up example number 2 in the topic of how to achieve a desired trim on a vessel. Now this is in the area of ship stability, and this is of course advanced ship stability for mates and masters. So if this is the first video you're watching, do not do so. Please make sure you watch all the previous 55 odd videos I've made on ship stability. The links are in the description section below. Make sure you watch all the videos to get a good understanding of the topic before you start watching videos on advanced ship stability. Alright, so let's get started with today's question. The question says that motor vessel Hindship is in dock water of density 1.007 tons per meter cube, and it is at a draft of forward 7.62 meters, aft 7.94 meters. So the vessel is kind of trimmed by stern. She has to load 450 tons of cargo. You have to calculate the position with respect to aft perpendicular where this weight should be loaded so that she would be trimmed 1 meter by stern on completion. So currently we'll find out what is the trim, and then we have to find out how we can achieve the desired trim of 1 meter. A few things that you have to note is, of course, firstly how much weight you have to load, that is 450 tons, the drafts which are given forward and aft. But the most important thing for you to note here is the density of the water in which the ship is currently floating in, and that is 1.007. Now why this is important is because the hydrostatic tables that we'll be using to obtain the information or essential information like displacement, MCTC, LCB and LCF are all for a density of 1.025, that is the seawater density. Now here the question is based in dock water density of 1.007, so you have to make certain adjustments to your calculation to make sure you're finding out the correct values. Alright, so let's get started. Let's get started by finding out the initial trim and the mean draft. So the forward and the aft draft is given to you, and the difference between the forward and the aft draft, always take the bigger number and subtract it from the smaller number, will give you the trim. So of course if the forward draft is more, the trim will be by head, but if the aft draft is more, the trim will be by stern. Now here in this case, this should be difference between forward and aft draft. So of course the aft draft is more, 7.94 minus aft draft minus forward draft is giving you the trim of 0.32 meters. Now of course because the aft draft is more, the trim is by stern. To find the mean draft, what you have to do is basically add the two drafts together, the forward and the aft, and divide it by 2, which will give you your mean draft of 7.78 meters. Alright, now you have to find out the LCF or the longitudinal center of flotation for the mean draft of 7.78 meters. Now because you don't have the hydrostatic draft yet, you will use the mean draft as a draft to find out the LCF value. Alright, so let's get started. How do you do that? So basically you can see you have to go into the hydrostatic tables for MV Hindship, and from those tables you have to find out the LCF value for 7.6 meters of draft or 7.8 meters of draft, because 7.78, which is the required mean draft, lies between these two values, and the hydrostatic tables doesn't provide values for the exact draft of 7.78. So let's go into the hydrostatic tables here, and you can see here the hydrostatic tables. We have 7.6 and 7.8 as the draft, but we don't have 7.78. So against these we'll find out the LCF values, which is the longitudinal center of flotation values. We'll note these values and go back into the calculation. So once we've got these values, we have to interpolate to find out the LCF value for 7.78. So how do you do the interpolation? Well, let's say for a difference of 0.2 meters, which is the difference of draft between 7.8 and 7.6, the difference in the LCF is 0.199, which is the difference between 70.979 and 70.780. But you need the LCF for a difference of draft of 0.18 meters. Why 0.18? Because 7.78, which is the required draft, minus 7.6, which is the draft that is there in the hydrostatic tables, that is 0.18. So you have to find out the correction that you will be applying to the LCF value of 7.6 to get the LCF for 7.78. So once you do a cross multiplication, you get a correction value of 0.1791. Now you can see as the draft increases from 7.6 to 7.8, the LCF value is decreasing. Therefore, as the draft will increase from 7.6 to 7.78, the LCF value should decrease. So the LCF value for 7.78 will be LCF value for 7.6 minus correction value, and you get the required LCF value for a draft of 7.78 meters. Now you will take this LCF value and find out the correction that you have to apply to the aft draft to get the hydrostatic draft, because that is our purpose. Our purpose is to get the hydrostatic draft. So trim multiplied by LCF divided by length between perpendicular, or LBP, will give you the correction. Trim, you have in the question, you have just calculated is 0.32 meters. Alright, just you calculated above 7.94 minus 7.62. The LCF value you just now found out. And where do you get the length between perpendicular value? Well, you have to go back into the hydrostatic tables. And here, at the beginning of the hydrostatic tables, you can see here, the length between perpendicular, or LBP, value is given as 143.16 meters. Now because all the calculations here involved are in meters, we will be taking the meters value and going back into the calculation. So I have put this value here as 143.16. Once we put that in, we get the correction as 0.158, which we always apply to the aft draft. We subtract it from the aft draft to get the hydrostatic draft. So the hydrostatic draft we get is 7.782 meters. Alright. Now we take this hydrostatic draft of 7.782 meters, go back into the hydrostatic tables and find out the displacement value. So this is the symbol for displacement. It's like a triangle shape. This is indicating displacement. So again we go back into the tables, we find out the displacement values for a draft of 7.6 and 7.8, and we carry out an interpolation to find the displacement value for 7.782, which is the hydrostatic draft. Alright, so we go back into the tables, find out the value for the displacement value. Here you can see, and we go back. So this is where we find out the values. The interpolation is similar. 0 for a difference of 0.20 meters of draft. The difference in displacement is 468. This is 16161 minus 15693. So for a displacement difference, for a draft difference of 0.182 meters, what will be the change in the displacement? Cross multiplication gives you a correction value of 425.88. You can see as the draft increases, so does the displacement. So the seawater displacement for hydrostatic draft of 7.782 meters is, you will add this correction value to the displacement for a draft of 7.6. So you will add it 1 to 15693 and you will get the displacement. Now remember, I told you the hydrostatic tables are for a density of 1.025. This is clearly mentioned here. You can see on top it's mentioned here. So we cannot use this displacement for our calculations. This is for 1.025. That's why I've written seawater displacement. You have to find the displacement in density 1.007, and that's why I said make a note of this figure, because this is the question is saying your vessel is in dock water of 1.007. So if 1.025 gives you a displacement of 16118.9, what will be the displacement for 1.007? Simple cross multiplication will give you a new displacement. This is the displacement for 1.007 density. Alright, so for this similarly, as you found out the displacement, you will also find out the values of MCTC and longitudinal center of buoyancy, or LCB, from the hydrostatic tables by carrying out an interpolation. So you go back to the tables, find out the MCTC, moment to change trim by 1 centimeter, and LCB, or longitudinal center of buoyancy. So you find out these two values. Alright, make a note of these values, go back into the calculation. You see I have written these values here, and you will do an interpolation to find out the MCTC value and LCB value for the required hydrostatic draft of 7.782 meters. The interpolation is similar to previously. For a draft difference of 0.2, the difference in MCTC is 2.8. This is nothing but 194.6 minus 191.8. So what will be it for a difference of the draft of 0.182 meters? The MCTC value increases with increase in draft. So when you find out the correction to MCTC, you will add it here to the MCTC for draft of 7.60 meters to get the MCTC for draft of 7.782 meters. So this is the MCTC value. Similarly, you will find out the value for the LCB by doing a cross multiplication or an interpolation. The correction value will be 0.045. This time you will subtract it, because you can see as the draft is increasing, the LCB value is decreasing. So you will subtract it, not add it, and you get the LCB value for a draft of 7.782 meters. Alright, these are the values you have to highlight. Now remember, you have got these values for seawater, not yet for dock water of 1.007. So for seawater it is 1.025, and that is, these are the values corresponding to the seawater density, because you have simply taken it from the hydrostatic tables. Now to convert these values, you have to do similar to what you did for displacement, but you will be doing it only for MCTC. So for MCTC, to get the MCTC in dock water, you have to multiply it by the MCTC that you get for seawater, multiplied by 1.007 and divided by 1.025, just like you did for the displacement above. You can see for the displacement above here, this is what we did, isn't it? You have to do the similar thing for this question for MCTC as well, and you get the new MCTC, and this is in dock water of 1.007 tons per meter cube. This MCTC was in 1.025, which is not what we require. However, for values of LCB, LCF, all the values which are only in meters, such as LCB, LCG, and LCF, you don't have to do any calculation or any interpolation or conversion. So this value will hold true for both 1.025 and 1.007. Remember that all the values which are only in meters will be good for both densities. So once you found out the value, you know the total trim is 0.32 meters, the initial trim is 0.32. Total trim also equals LCB minus LCG divided by MCTC by 100 multiplied by displacement. Your objective here is to find LCG, because this is the only thing that is unknown to you. You know LCB value, you know the current trim, you know MCTC, and you know the displacement values. So simply put in the values in the equation, isolate LCB minus LCG. So take these values here, this value will come here, this is giving you this equation here. LCB minus LCG will be 0.386. You know the LCB value already as 72.645. From above you have calculated it. So the LCG will be 72.259. And since it's in meters, this will also hold true for both densities. Now the original displacement given to you is 15835.8. To that you have to load 450 tons, and the final displacement is 16285.8. That will be your final displacement. Now 15835.8 is your displacement. As you can know, this is in dock water. Alright, so this displacement is dock water. Do not take the seawater displacement. This is cargo to load is then 450 tons given to you in the question given, and this is the final displacement is 16285.8. Now to get the other parameters, you have to take this displacement, which is in 1.007 tons meter cube. You have to convert this back to displacement in seawater to find out the parameters of MCTC and LCB for the final loading condition. Now this displacement 16285.8 is in dock water density of 1.007. You have to find out the answer in seawater 1.025. What is the displacement in seawater? 1.025, because you have to go back into the tables and find out the values of MCTC and LCB after the vessel has finished loading. Alright, so the ones that you found out, MCTC and LCB, was for a condition when the cargo has not loaded. But once the cargo is loaded, you have to find out new MCTC and LCB because it will change after you finish loading cargo. To do that, you have to go into the hydrostatic tables. But the hydrostatic tables is for seawater density. That's why this displacement has to be converted for displacement in seawater. So you will do the opposite of what you did before, because 16285.8 is for density 1.007. So for 1.025, you will multiply 1.025 here, and this will come down here, and that is what the equation says. So the displacement you will be using to enter the hydrostatic tables is 16576.9. So for taking this displacement, you go back into the hydrostatic tables 16576.9. So when you go back, you can see 16576.9. 16576.9 lies between here and here. This is where it lies. So you have to note down the parameters. These are the parameters. So MCTC values, LCB values, these are the parameters you have to note down. Alright, and then interpolate it to find out the values. So you go back here, this is what I have done. So the displacement, this is the required displacement. So for this you have to find out the required draft, the hydrostatic draft, the MCTC as well as LCB. The interpolation is simple. You can see here I have shown you the interpolation for a difference of displacement of 474. The difference in the draft is, or difference in the MCTC is 2.8. We don't have to find the draft, we have to find the MCTC. This is 197.4 minus 194.6. So for a difference in displacement of 415.9, what will be the change in the MCTC? So you can see here the correction to MCTC is shown. As the draft is increasing or the displacement is increasing, the MCTC will increase. So you will add this to the MCTC for 16161 displacement, and you find out the MCTC for displacement of 16576.9. Similarly, you will find out the LCB values as well through interpolation. You can find out the correction. This time the correction will be subtracted because you can see as the displacement is increasing, the LCB is decreasing. So you will subtract it and you will find out the LCB for the same displacement 16576.9. Alright, now this MCTC that you found out is because it is for seawater. You will be converting it into dock water MCTC because you need it for a dock water of 1.007. So this is the part that I was telling you at the very beginning. You have to note down the density to make sure you keep coming back and keep converting the values for the required density. The LCB values or the LCF values or all that, they don't matter because they are in meters. They will be unchanged for different densities. But values like MCTC will change with changing density, and that's why every time you find out the value from the hydrostatic tables, remember that it is for 1.025 density and you need it for a density of 1.007. So to convert the MCTC from 1.025 to 1.007, you will multiply it by 1.007 and divide it by 1.025 and find out the final MCTC. So this is the final MCTC, and this is for dock water density of 1.007. This is the final LCB. Alright, then you know that you need a required trim of 1 meter. That is what the question says. Your current trim is 0.32, but you need a required trim of 1 meter. So you have to find out where you will load these 450 tons to make sure that you get the required trim here. Alright, so you know the trim, you know it's equal to LCB minus LCG multiplied by MCTC by 100. Again, you are finding out the final LCG after the loading operation is over, because you found out the LCB, you found out MCTC, you also know the displacement. And this is all for, remember, this is all for 1.007. So the displacement you will use will be for 1.007. The MCTC, the LCB, all should be for 1.007. So don't use the displacement of 16576.9 because that was used to obtain the hydrostatic tables, the values from the hydrostatic tables. Your original displacement for a density of 1.007 after loading is finished is 16285.8 as you see here. Alright, so keep a note of these things. Do not use the wrong displacement. So now you can find out the LCG like you did before, because you know your LCB. LCB was 72.594. You subtracted it and then you've got the final LCG value. Alright, you've got your final LCG value. Now all you have to do is find out from where you have to load the cargo. So you will take your initial displacement 15835.8, and this is before cargo was loaded. This is again for a density of 1.007. You know your initial LCG that you found out, you will multiply it and you will find out your longitudinal moment. You know you have to load 450 tons of cargo. This will give you your final displacement. You don't know where it is to be loaded from, so you will call it X and you will get 450X. Because you will be loading, the longitudinal moment will be added. So this is your final longitudinal moment. So your final LCG will be equal to final longitudinal moment divided by displacement or final displacement. But you already know your final LCG. What you don't know is from where the cargo is to be loaded. So your final LCG is 71.405. You got this from here. Simply take this value here. Then once you multiply these two values, take this one here. You got 450x. Then you will divide 450 here. The x that you get is 41.352 meters. And you get that forward of half perpendicular. Now because all these values, the LCB values, the LCF values, they are all given with respect to their distance from the half perpendicular. So when you find out the distance where the cargo is to be loaded or distance where the cargo is to be discharged, you will always find it out with respect to half perpendicular. Only if the question asks you that find it out with respect to the forward perpendicular, what then you will do is you will subtract this distance from the length between perpendicular to find out the distance from forward perpendicular. Otherwise, the distance that you will calculate will always be with respect to the half perpendicular, because all these values LCB, LCG, LCF, all they are given with respect to the position from the half perpendicular. So I hope guys you didn't get too confused. I took up this question because here there is a issue of changing density. Because if the density is 1.025 in the question, then it's not that complicated. It's simply a matter of getting the values from the hydrostatic tables and interpolating it. But if there is a different density involved, then you have to be very careful as to how you are entering the hydrostatic tables, and when you find out the values, how do you convert it for the required or the given density. So remember, whenever you enter the hydrostatic tables, if you are entering with the hydrostatic draft or with the displacement, that should be for the displacement should be for the seawater. All right, that should be the seawater displacement. Once you get the values from the hydrostatic tables, you have to convert those values back for a dock water density. But you only convert those values which are not in meters, like MCTC. But all the values which are in meters will be same irrespective of density. But you have to enter the tables with the displacement of given in the seawater. So let me know if there's any part that you didn't understand. If there was any confusion, write it in the comment section and I'll be happy to answer it. Thanks guys.